Let's talk about some testing techniques, okay? So it turns out when we go and we try to test or exercise, there's a set of techniques we can do to help us pick good cases, help us pick good scenarios under which we'll test our system. So when I say a test case here, for something like square root, it would be a third input. Give it an input of 4, give it an input of 1, give it an input of 3, I give it an input of -1. Those are test cases. How do I pick my test cases? Is it possible logically to fully test? Is it possible? Is it feasible, I should ask? Put aside the issue of logic. Is it feasible to fully test the square root against all possible numbers? No. It's just, it required many times longer than the universe has ever existed, and, back before the first lungfish emerged from the primordial soup, if that lungfish had started testing it still wouldn't be good. Fancy that. Imagine that. Here, we instead try to pick our test cases artfully. We try to pick the important ones, the ones who are likely to show problems. So let's talk about some techniques here. The first one is all I'm going to really cover in any sort of texture, and that's equivalence partition or boundary value testing. These later ones we'll talk about in a later course at IT 371, and I welcome you folks there. You'll be entering with a leg up, since you'll be less likely to give me 3 thumbs up for some of the testing. Let's talk though about equivalence classes and boundary value testing. So the idea here is, folks, that often our software, whether we're talking at a high level or at a low level, whether we're talking about a particular function like square root, or whether we're talking about the broad functionality of some system, a system that allows us to make ticket reservations, confirm seats on planes. It deals with inputs and it generates outputs. It does things that are characteristic of certain classes of inputs. So if we're dealing at a high level with something like reserving seats, you might group seats on a plane into a set of classes. So there's, those seats in the first class or business class cabin, and then there's coach seats. And maybe the first class seats don't have to deal with seats in the center. They only deal with window and aisle, but the coach might have to deal with all 3. And here we might, instead of testing that our system works for reserving every single seat in turn, we might instead choose to focus our efforts, marshal our efforts, our limited resources on testing really well a small number of seats that are in some sense representative of others. So for example, we might test at least 1 window seat and 1 aisle seat in the first class cabin. Maybe we'll go further and do it the first row of the first class cabin and the last row of the first class cabin. And similarly something for coach class. Want to have at least 1 of each type of seat, and then maybe those at the back of the plane, those at the front of the plane, what have you, to make sure it's working properly. So the idea here, folks, is to kind of think of the input. It could be input at this level, or it could be input to a function, like for square root. We think about equivalence classes. We think about sort of classes of input that are in some sense similar. And we try to select a representative from each class, at least 1 representative. And then we test the boundaries of each class. We test the things that lie between them to make sure they're resolved the right way. Because often those are where we make a lot of mistakes, or cases where inconsistent reasoning is often okay. You think about input on web form, something like that. We might test non-existent or empty input. We might test a single input item, or perhaps a series. Okay. So let's talk about this. So give me some examples. So let's take square root. What are some equivalence classes? Some things that for square root we kind of expect if it's right for one of them, it will be right for the whole set. Square root. So if I have a square root, and it takes a double as an input, and it returns a double. Give me some equivalence classes. Things that, again, if I pick one representative, I kind of anticipate if it works for that, it probably works for the other. Okay, integer perfect square. Great example. If it works for 4, probably works for 9. Probably works for 16. Probably works for 1024. Probably works for 65,536. It probably works in general for perfect squares. Okay, so those are good. What's another equivalence class? Negative numbers. If it handles one negative number properly, say minus 2, it probably handles other negative numbers properly. And that handling may be saying, invalid input, and that's fine. If that's part of its definition of how it should work, that's fine. Or if it returns a complex number, it's also fine. Okay, what's another equivalence class? Have we covered them all? Non-perfect squares? Non-perfect squares. Non-perfect by extension positive squares, so that's good. Or do those have to be integers? No? Okay. So imaginary numbers? Yeah, if it is defined such that it needs to. Again, this gets back to requirements. How is it defined? What is the comment on how this works? What's a legal input? That would need to be considered here. But you've given some good examples here. Here perfect squares. 1 and 0 are a little bit odd. Why are they odd? Why do we say that they're sort of special? Well, ladies and gentlemen, we apply square roots and we get the same thing back. They're fixed points of the square root function. Fixed points of the square root function. They're a little bit different perhaps in the operations that take place. So these would be examples of square root inputs. If you didn't have those, I wouldn't dock you, much for that, certainly. Here's some other examples of equivalence classes. If you're asked to enter a number and a valid input is between 1 and 99, you might enter things within that range, but so 1 to 99, but you might also enter things that are deliberately outside of it. And what I want to highlight here, folks, is particular representatives, the so-called boundary values that are just on the edge. Like 0 is just one off from a correct value, and similarly, say 100 is just one off. So you want to make sure that 0 and 100 don't work. And that 1 to 99, you want to check at least a couple of them that it does work. Negative numbers here, we want to make sure. We want to give letters, another alphanumeric characters. It's a nasty world out there, folks. People misunderstand, they're malicious and try to do things. You want to be proactive and handle these things. Okay, so similarly, if you're asking for the first letter of the name, first character is a capital letter, first character is a lower letter. Certainly in our culture, we want to check those things. But folks, not all names start with letters. Actually, there's some names for the San Bushmen in southern Africa that start with ticks or what have you, and they indicate sounds like that. And maybe this is someone who's retained their name from the Kalahari. So you want to be able to handle other cases, and if it's defined such that only letters are first, apply. We have to handle them, and we have to test it at least to make sure it correctly, gracefully handles cases where it's not. Okay, so these are some cases of equivalence clauses and some examples of sort of borderline cases. Okay, so what would be a borderline case for a square root function? Give me a borderline case between things that are handled in very different ways. Well, 0 would be a good one. Zero would be a good one, for example, for that. Okay, time is running short, and I'm hesitant to start this up. Maybe I'll just pose as a question. Okay, suppose we have a piece of code that we want to compute a factorial. People know what factorial is? So if I write 3 factorial, tell me an equivalent expression.
3 times 2 times 1.
Exactly, 3 times 2 times 1. So suppose we were given this code. First of all, is this code correct? How would we, and remember, this is the whole purpose of testing. How would we develop confidence whether or not this code is correct? Look at it. Try running a test case in your mind. What's a test case that you might run based on what we've just talked about? Okay, so 3. Is this code correct for 3? That's the representative of 1 equivalence class here. Is it correct for 3? What happens if we give it 3? So it will stop when this reaches 0. So we run it. The while, does it execute the first time? And what happens here? N was 3, now it's, okay, so we have back times equals 2, is that correct? No, that's not correct. Okay, so, you know, we might end up going and fixing that, but we might also think about other boundary conditions. Another possibility would have been to try it with 0, for example. Would this work for 0? What would happen with 0? It would stop. How do you give it at 1? What will it give for 1? For 0, what will it give? 1. For 1, what will it give? Is that correct? Yeah. How if we give it a negative number?
Carry on forever.
Sorry?
Will it carry on forever?
Yeah, carry on pretty much forever. It will eventually wrap around, but probably you'll be buried by that time or something like that. Yeah, it'll essentially crash. It will suck up cycles uselessly and not work here. Okay, so we might consider refactoring this to handle these vulnerabilities and further develop it, but we'll follow this this later. But when you look at some code, think about what are the common cases, and at least test one of those and test the boundaries between them. And that will put you, ladies and gentlemen, in good stead for the problem set, which again is due Saturday evening, okay? Just before midnight. This Saturday, 12. Thank you.